If a function f is not continuous at least in one of the boundaries of integration, in this case, the integral is called second type improper integral. In this part, I give 3 convergence tests for second type improper integrals, and the first test is called comparison test or direct comparison test. Assume that the function f is greater than g and they are both positive functions on the interval ab. Here you see that they are not continuous at the point a. This is why this is called improper integral, by the way. And if we have two cases, the first case, if improper integral of f, which is the greater one, converges, then improper integral of g, which is smaller one, must converge. Let's try to understand this case. Assume that you have a known integral. You know the behavior, you know the convergence of this one. Okay, and you know that the greater one is convergent. What does it mean? The answer of greater one is a number. What can we say about the smaller one? If the greater one is a number, smaller one must be a number. This is why if the greater one converges, the smaller one must converge. Look at the second case. Again, considering these inequalities. Assume that improper integral of g diverges. In this case, improper integral of f also diverges. We have a known integral. Okay, we have a known integral. We know the convergence of this one, and we know that the smaller one, which we know, diverges. What does it mean? We know that the smaller one, the answer of smaller one is infinity. This is why we can say that the answer of greater one must be infinity. The answer of greater one cannot be a number, since this is greater, right? This is why we have the second case. Let's try to understand these cases by some examples. But before starting examples, we have a nice note here. As you see, in this case, the functions are not continuous at the point A. This test still works even if they are not continuous at the point B instead of A. Okay. The number 1, the endpoint 1, makes denominator 0 and also makes integrand undefined. This is why this type is called second type improper integral. So I think it's important to remember the graph of arctangent x. In this case, this is the graph of arctangent x, and as you see, when x is in this interval from 0 to 1, 1 close and 0 close, 1 open, for this interval, we know that by this graph, arctangent x is actually greater than or equal to 0, right? So this is why we have this inequality, e to the power arctangent x. I want to create the integrand of the question, is greater than or equal to e to the power 0. Okay, so by this step, if you divide each term by 1 minus x, you have this inequality. Okay, and we know that e to the power 0 is equal to 1. So this is equal to 1 over 1 minus x, right? And we know that, do we have an information about the integral from 0 to 1 dx over 1 minus x? Do we have information about this integral? Yes, we have information. We know that this is a divergent improper integral. By p-test, we solved this problem before, I think. So let me show why this is divergent. We know that 1 over x, the integral from 0 to 1, 1 over x is a divergent improper integral, and this one is greater than 1 over x. This expression is greater than 1 over x. If this improper integral diverges, then the greater one must be divergent. This is why this is a divergent improper integral. So again, look at the question. This is the smaller one, right? Integral from 0 to 1, we know that this is divergent. If the smaller one is a divergent improper integral, the greater one, which is the question, must be divergent. The answer of this is divergent improper integral. Second convergence test for second type improper integral is limit comparison test. Assume that the functions f and g are continuous at this interval, but be careful, they are not continuous at the point A. This is why this is type 2 improper integral. And assume that a limit of f over g is equal to L when x tends to the point A from right. We have three cases as we had for type 1 improper integrals. The first case, if L is a finite positive number, then if improper integral of g converges, then improper integral of f must converge. Or if this improper integral diverges, then improper integral of f must diverge. So what do we understand by this case? If the answer of this limit is a finite positive number, the convergence of these two integrals is the same. They have the same convergence type. They both diverge or they both converge. If the answer of this limit is equal to 0, and if improper integral of g converges, then improper integral of f must converge. This is the second case. And the third case, if the answer of this is equal to infinity, and if improper integral of g diverges, then improper integral of f must diverge. Okay, we will have a question, a function in the integrand, and it is requested to find another function. It is requested to create another function, which is g. Okay, so we will create this function and we will find the limit value. Then we will comment. Let's look at the questions. By the way, we have these cases also. If f and g are not continuous at the other endpoint, which is b, this test is still working. Okay. Now let's look at this example. Determine whether the following integral converges or diverges. Let me first write f. F is the integrand 1 over 1 minus ln square x. By the way, this is type 2 improper integral. How do we understand? Look at the upper bound of integration. When you plug this value into x, you see that you have 0 in denominator. This is why it's called improper integral of second type. This is f. What about g? So we should create another function g, and we should look for limit of f over g when x tends to the point E, since E makes the integrand undefined, from left. Okay, this is the point 1 and this is the point E. This is why we approach from left. Limit of f over g is equal to, so I should write a function for g. So let's say g is equal to 1 over e minus x. You actually can write any function. This is all up to you. But be careful about the answer of this limit. If it's useful, if the answer is useful according to limit comparison test, then this is okay. You can write any g function. If it's not working, you must change the function g. So let me write f over g here. So f over g becomes e to the e minus x over 1 minus ln square x. When x tends to the number e from left, as you see, you have 0 over 0 case, right? 0 over 0. This is why you have to apply L'Hopital's rule. Let's apply L'Hopital's rule. When x tends to the point E from left, derivative of numerator is equal to -1, derivative of denominator is equal to -2 over x, ln x. When x tends to the point E, you have E over 2. This is L, right? E is a number which is greater than 2, and you have 2. Finally, you get the L. Let's look at this test, limit comparison test. We have a positive number, as we stated here, right? We have a finite positive number. This is E over 2. So the behavior of improper integral of G and F is the same. They both converge or they both diverge. So can we say anything? Can we say anything about the improper integral of G from E to 1? This is from E to 1 improper integral of G dx over E minus x. So what can you say about the convergence of this improper integral? This is actually divergent. How? We know that 1 over E minus x is greater than 1 over x for x is in close interval 1, open interval E. For this interval, we have this inequality, right? And we know that this improper integral is divergent. If the smaller one is a divergent improper integral, the greater one must be divergent. This is why this improper integral of G is a divergent improper integral. And by limit comparison test, improper integral of f from 1 to e and improper integral of g from 1 to e have the same convergence type. Okay. What do we get about the convergence of this one? We get that improper integral of g diverges. Since this is a divergent improper integral of f must diverge. So we get the answer. The given improper integral is divergent. This is all. Let's look at the next test, which is called also limit comparison test for second type improper integrals, but this is the modified version. This is also called Q test. In this case, what is the difference? We take g of x as g minus x minus a to the power minus q, okay, for this limit expression. So this is g. And we comment on the values on the answer of this limit expression. According to the answer, we have two cases. In the first case, we say if L is 0 or any positive finite number, and if Q is smaller than 1, in this case, the given improper integral of f converges. Second case, if L is not 0, it can be infinity, it can be any finite number, and if Q is greater than or equal to 1, in this case, the given improper integral diverges. Of course, you have this test when the function f is not continuous at the other endpoint of integration b. Now let's try to understand this test by some examples. Determine whether the following integrals converge or diverge. We have two integrals actually. So what can we say about the first one? Is it an improper integral or not? Yes, this is an improper integral. The point 1, which is in between 0 and 2, makes denominator 0 and makes the integrand of the function undefined. This is why this is type 2 improper integral, right? This is type 2 improper integral. So if we have type 2 improper integral, and if one point in the interval makes integrand undefined, we have this case, right? We have this case. So this improper integral is equal to integral from 0 to 1. Since 1 makes denominator 0 and the integrand undefined, I have to choose 1. You have dx over x minus 1 square plus, this is the first part, and integral from 1 to the other endpoint 2 dx over x minus 1 square. This is the first part. We first break the given improper integral into two parts. If these two improper integrals both converge, in this case, we say the given improper integral also converges. If one of them diverges, it is enough. If one of them diverges, then we say the given improper integral diverges. Okay, what do we say about the first improper integral? Integral from 0 to 1 dx over x minus 1 square. This is second type improper integral. And I want to use modified limit comparison test or Q test. Let's use Q test, okay? And let's say Q is equal to 2. So in this case, limit when x tends to 1, since Q is 2, we have x minus 1 square over f. What is f? F is 1 over times f, times f. F is 1 over x minus 1 square. So you have x minus 1 square here. And the answer of this limit is equal to 1. This is L. L is a finite number and Q is greater than. Let's look at the test again. Q is greater than 1. Okay, Q is greater than 1. And L is a non-zero number. In this case, the given improper integral diverges according to this test. Since Q is greater than 1, okay, and L is not equal to 0, the given improper integral diverges by modified limit comparison test or Q test. Now we are ready to look at the second example, integral from 1 to e dx x minus x ln x. Okay, what do we say about this improper integral? First, let me write down f. F is 1 over x ln x. I first want to use limit comparison test, okay, not modified version. And I want to write a function g. Let's say g is equal to 1 over ln x. I first want to look at f over the limit of f over g. Limit of f over g is equal to limit of 1 over x, as you see. So this is equal to 1. Of course, when x tends to 1 from right, look at the endpoint 1. This point makes denominator 0, ln1 is 0. This is why this is second type improper integral. And the limit of f over g is equal to 1. So this is the number L. So this is the first case of limit comparison test. What do we understand by this limit comparison test result? We understand that the convergence type of improper integral of f and improper integral of g is the same. They have the same convergence type. Okay. What can we say about improper integral of g? What can we say about improper integral from 1 to e dx over ln x? Now let's examine this question. If we have an idea about this, then we can easily say something about the convergence of the question. In this step, I want to apply modified limit comparison test or Q test to improper integral of g. Let's say Q is equal to 1. This is x. This part is coming from the formula, this limit comparison test. Let's say Q is equal to 1. So for g, we have 1 over ln x. So let me substitute this expression. Then we have x minus 1 over ln x. When x tends to 1, you have 0 over 0 case. If you apply L'Hopital's rule once, you get the result 1, which is not 0. This is L. This is L, is not 0. And Q is 1. And this is why this improper integral of G from 1 to E diverges, right? Is diverges. I applied Q test again. I took Q as 1 and L is not 0. This is why improper integral of G diverges. What I told you before, we discussed that improper integral, the convergence of f dx and g dx is the same. They both converge or they both diverge by limit comparison test. Since this improper integral diverges, the given improper integral must diverge by limit comparison test. This is all. I have a final example, very nice example. So what can we say about this question? As you know, we have infinity in the upper bound of integration, and also the lower bound 1 makes denominator 0 and the integrand undefined. So this is the mixture of type 1 and type 2 question, type 2 improper integral. In some books, this is called type 3 improper integral, since this includes type 1 and type 2. So in order to solve this problem, I first must break this improper integral into two improper integrals. And the first one is from 1 to any point. Let's say 2. dx over x square, square root of x square minus 1. This is the first part. And the second part from 2 to infinity. dx x square minus 1. So we have two kinds of improper integral. This is second kind and this is first kind improper integral. So I will apply some tests and determine the convergence of these improper integrals. Let's call the first one as A, the second one as B. Let's start to discuss the part A. I want to apply modified limit comparison test to part A. In this case, I want to take Q as 1 over 2. So limit when x tends to the point 1, which the integrand is not continuous there, from right, x minus 1 to the power 1 over 2 times the function, the integrand. This is 1 over x square, square root of x square minus 1. Okay. So why do I prefer to choose q as 1 over 2? Since the power of this expression is 1 over 2, I especially choose the power of q. I especially choose the q as 1 over 2. So you can write this as 1 over 2. If you simplify this limit, you get 1 over square root of 2. This is L. L is 1 over square root of 2. Q is 1 over 2 by limit comparison test. For second type improper integral, we say that A is convergent improper integral. What about the second part? This is type 1. For type 1 improper integral, I also want to use modified limit comparison test. Let me first write the expression. X tends to infinity. Since this is type 1, I take p as 3. So we have x cubed. And this is the function f, x square, square root of x square minus 1. So this is 1 when x tends to infinity. And p is 3, as you see, p is 3, which is greater than 1. What else? So I used modified version of limit comparison test. So this is L and this is P. If you remember the rule, you say that the improper integral of P also converges for modified limit comparison test, or P test, for first type improper integrals. If these two improper integrals both converge, the given improper integral also converges. This is all.